Let's carry on. We've done question 9, which is the electron configurations. Let's now have a look at question 10. They say determine which of the following compounds are ionic, polar covalent, or pure covalent. Just before we start this, let's recap it. Okay, remember, how do we find that what they are? We look at what we call delta electronegativity. If you wish, you could also have delta En like that. Okay, doesn't matter which way ever you want to choose it. So what we've got here is change in electronegativity. What do? They have said to us KCl, right? Which means we've got a potassium and a chlorine ion linked. So we've got a bond between there. Why? Because they're together. It's a compound, right? We've got a potassium and a chlorine stuck together. So they are glued. How are they glued together? Well, the electrons have been shared or whatever captured. We need to look. We look at the electronegativity. So we look at the electronegativity. Okay, Kevin learned to write. Electronegativity, okay, of the chlorine. Okay, let's just go and have a look at the electronegativity of the chlorine. And we say, all right, chlorine is 3.0. Okay, where did I find that number? Go to your periodic table, look next to fluorine. Okay, fluorine has got a number of 4.0. Okay, you'll see all the other numbers by now. You know it's the atomic mass, etc., relative atomic mass. And you've got the element number as well, which is there, right? Which is the number of protons. Remember that? The element number of protons, which for the elements is the same as electrons because the element is not charged, right? So therefore we say, right, if you look, you'll see the number 4.0 next to fluorine. That is its electronegativity. You will see that it is the highest of all of the elements, right? Which means it's the greediest. It's the one that's going to pinch electrons more than any other, right? So, and chlorine not far behind at 3, all right? Would chlorine and fluorine bond? Yes, they actually do, okay? But let's not get there, all right? So we say to ourselves, okay, oxygen and fluorine do, we've seen that before. Let's have a look here. Then potassium, the electronegativity of potassium is 0.8. We subtract them because delta electronegativity, delta means change, all right? It's always positive, all right? So we go here and this is 2.1. Now, how do we decide? Remember the table. This is change in electronegativity here. If it's 1.7 or above, that is an ionic bond, okay? And if it's 0.9 and below, this is going to be a covalent bond. And if it's anywhere in between 1.7 and 0.9, it's going to be polar covalent. Polar covalent means what? One side is negative, one side is positive. So this here is an ionic bond. Okay? It is greater than 2.7, so it puts it to 1.7, so it puts us up there. Okay? Next, let's have a look, and they say water, H2O. Right, so let's have a look. Just move my page up a bit. Water, H2O. So we've got an H and an O and another H. We only look, remember, we only look at the one side of the bond. All right? So we say, right, electronegativity of oxygen, and I've got it down here, is 3.5. Electronegativity of hydrogen is equal to 2.1. Delta electronegativity is equal to 1.4. Okay? Therefore, where does it put us? It puts us over here. Right? If it's there, it means we are what? We are polar covalent. So it's polar covalent. And what happens in a polar covalent molecule? What happens there is you've got O, the H and the H, all right? It means that the one side is negative, delta minus, delta plus, because why? The electron is here more than there. Spends more time there than it does here, right? Which makes that side more negative, all right? So therefore, that's why it's polar. Polar means it's got a plus and a minus pole. Same as a north and a south pole of a magnet. Not the same, okay? But similar concept to the north and south pole of a magnet. So yes, if the one side of a molecule is positive, if we've got, for example, this over here, we've got this side, and let's say this side is negative and this is positive, it means that if there's another negative around, it's going to move away from this side. If there's a positive, it's going to attract to this side, right? So this side is the one with the higher electronegativity because it's negative. It pulls the electron into this orbit more than this side. Ionic means that the electron is always here and the electron is never there, right? It means it's pure ionic. Pure covalent is when we have these guys, right? Two of the same, we're going to get to that now. Two of the same over here, they share the electron absolutely. There is no poles because the electron half the time and half the time there's no pole. Your diatomic gases are these. Always remember that, right? Okay, let's have a look at the next one, right? So what do we say? The next one, all right, let's just move it up. The next one is going to be, was water. The next one was lithium fluoride, correct? Lithium fluoride, we said okie dokie. LiF. So let's have a look. Electronegativity of fluorine is 4.0. Okay. Electronegativity of lithium is equal to, find it on your thingy. Okay. 1. So it's 3. Therefore, it's ionic. Ionic bond. So it means you're going to get Li plus 1, fluorine minus 1. Okay? They're going to be separate ions. Anion, another negative ion. There's my anion, and there's my cation. Right? Let's move along. Let's have a look now at oxygen. All right? Let's have a look at oxygen. What is oxygen? O and an O, right? And we know that it had a double bond, correct? From the electron configuration, we're going to get into those in a few seconds. All right, in fact, in the next question. But what have we got? We've got electronegativity of oxygen is 3.5. The electronegativity of the other oxygen, 3.5. Delta electronegativity, 0. Therefore, you can say that it is pure covalent bond, okay? Not even weakly polar, okay? Okay, then the last one is, they say CH4. Oops. CH4. It actually, guys, looks like this. Okay? This is the good old enemy of miners, coal mines specifically. That over there is methane. Okay? Methane, a gas, highly combustible. Coal mines, it used to ignite if there was a slight spark, and obviously a lot of people got killed in these gas explosions in coal mines. Okay, methane is there, and they want us to know what it is. So let's have a look. We say, now remember, we only do the one bond side, right? So we say carbon. The electronegativity of carbon is equal to what? Is equal to 2.5. The electronegativity of hydrogen, 2.1. Look what I wrote. C.1. Delta electronegativity is equal to 0.4. So it's less than 0.7. So it's covalent. Okay? The fact that there is a thing there is a slight pull on the electrons from the carbon. So the carbon pulls the electrons a little more than it should, okay? All right? There is a slight pull, okay? Now, let's have a look at question 11. Question 11, okay? Shift it up here. All right? Question 11, they say use Lewis diagrams to represent the following. Oxygen gas. Oxygen gas, right? Okay. Oxygen gas. Oxygen gas is O2. It's diatomic, right? Why? Because it's got the 2 there, which is the di, okay? In chemistry, di means there's 2 of carbon dioxide. There's 2 oxygens attached to the carbon. In fact, I think we're going to see this one. Yes, we are. Oxygen gas, okay. How do we draw these? What do we do? Well, first of all, the way I like to do it is I go and I say, right, my oxygen is over here. That's a very poor representation of an O, but let's have a look. My oxygen is over there, okay? I look and I say, what number is oxygen? Okay, count it and find where oxygen is, and we see it's number 8. Therefore, it must have 8 electrons. I start filling my shells. 1s2, 2s2, 2p, 4. Right? 4, 5, 6, 7, 8. Let me just tidy that up there. Can you see that? I say, how many electrons have I got here? Let me just go through this again. 4, 2, 2, 8 electrons ties up with the atomic number of oxygen, which is the number of protons, but also the number of electrons, because it's not charged. Okie dokie. Moving along. Let's have a look. What do we do next? We say, right. I say, right, let's draw one. Okay? Let's draw oxygen over here. First of all, I'm going to start, I always start at the top and I go cross, 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 cross. There's 4, okay? Because I'm filling up each shell. Remember the exclusion principle? You have to fill them up in the correct order. So we say right, and 6, 4, so I say right, and now I've got to put in those 2 there, correct? So there's my oxygen, okay? Now, I know because I've done it before that I'm going to have to put the other oxygen and rearrange it. So, but let's say we drew it like that, and then we go and draw our other one. I'm just going to draw it in with a different thingy, and I'm going to say, right, 1, 2, 3, 4, 5, 6, okay? So where are our bond positions, okay? The open parking areas are there, correct? Can you see that? Because there it needs an extra electron to fill it. So the open parking areas, there's 2 of them, correct? Okay, so what do we do now? Well, quite simple. We then say, oh, hang on, we've got to draw how these are going to bond, and we've got to show it. So we're obviously going to have to maneuver these around so that we can show it in a diagram. So let's redraw it. Here's oxygen, and I am now just going to change my structure slightly, not my structure, but I'm just going to put my full orbitals there, and I'm going to put my other oxygen on this side over here with my, okay, like that, correct? Because what do I want to show? I want to show how these bond. These 2 over here, let's just go to blue, these 2 over here bond, and these 2 over there bond, and what do we end up with? We end up with this. Just shift it up slightly. The oxygen's like that. There's my double cross there. Those orbitals are full, right? This one has moved across, and let's put in, I've put him in already. Let's put it in as the green. The green guys, you're full there. This guy has done there. So there is the bond, correct? So therefore we now draw that. That's now we've explained it. The last thing, just for extra, is that oxygen, we say, has got a double bond. Why? because 2 electrons, let me actually write it out properly, 2 electrons bond. Therefore, double bond. Yep, and if you had nitrogen, 1, 2, 3, that's a triple bond because you have 3 electrons bonding. Okay? Let's have a look at the next one they ask us. The next one, NH3 ammonia. NH3 ammonia. Let's have a look at NH3. Right, nitrogen first. Nitrogen, what number is nitrogen? Nitrogen is, and I say, okay, 1, 2, 3, 4, 5, 6. Nitrogen is number 7. Therefore, 1s2, 2s2, okay, that's 4, 2p3, correct? 3, 4, 5, 7. Let's just go through the process again. 1, there we go. Add them up, and you've got 7 electrons. There we go. Right? Now we draw the nitrogen. Okay, here's our nitrogen. We know, but how many we only draw, and I forgot to say it on the previous one, we only draw the valence electrons, right? The outer shell. We leave the inner shell alone because at this stage we don't include that in the bonding process. So how many electrons are in the valence electrons? There are 5 valence electrons, but the valency is -3. I'll show you now. Let's just recap this. Okay, let's put in our 5. I start here. 1, 2, 3, 4, 5. All right? That's just the way I've gone round. Now let's have a look. How many parking spaces? 1, 2, 3 parking spaces. That's my valency. -3. Okay? There's 3 parking spaces that we can use there. So what is the next step? The next step is now let's look at hydrogen. Well, hydrogen's a very simple one, we know. H, sadly, is only got over here 1. What happens is that all of those go into those parking. So 3 hydrogens can move in to that. Okay? So let's complete the task. And we say, right, nitrogen, let's just put it in the center. Shift it back to black first. Nitrogen, okay. And I've got to put 1, 2, 3, 4, 5. And now we put our hydrogens. We know that the hydrogen is going to share its electrons like that. Correct? Well, therefore, you get essentially N with an H, and they are all single bonds. Correct? Okay? They're all single bonds. Please note, okay, let me explain something. NH3, remember, we had that. All right, I'm just going to put my green dots in here, like so. Okay, we had H coming in like this, correct? Now, how do we form NH4? NH4, the ammonium ion. What actually happens is, can you see at the top over there, all right, we have got this pair of electrons. They are called a lone pair, okay, because they're not bonded to anybody. They are there, they were there with the atom right from the very beginning, okay? So they stay there. What happens next is then there's a hydrogen floating around. Never mind where he comes from at the moment, but there's a hydrogen floating around which is just a proton because the electron has gone, okay? So it could come from an acid, okay? But let's not get too technical. Let's not get too far ahead. But yes, an acid is a proton donor, but we've got this hydrogen floating around on his own, one single proton. He's positive, right? This side here is negative. What happens? They attract. So eventually, okay, we end up with something that looks like this. we end up with nitrogen. Okay, da-da-da, da-da, da-da, da-da. And we put in our hydrogens, okay? And this poor chap over there, he floats along and he put these guys in here. And he floats along and he forms a bond. Basically, he just goes and sticks to that, all right? And you can see here, this is now, well, it's nitrogen, NH4, but it's positive because there's an extra plus charge on this thing. Remember, these 3 hydrogens cancelled out the 3 negatives. Nitrogen was -3, hydrogens +1, times 3 of them is +3, -3, so it was 0. There is the ammonia is 0. But when we add an extra proton, we add an extra hydrogen on, we say, okay, +1, it becomes +1 charge. Okay? Straightforward, simple as that. All right? The next one they want to see CO2. Okay? So let's go and look at CO2, carbon dioxide. Okay? It is usually a gas, unless you have dry ice for your party. All right, CO2, carbon. Okay. Number 1, 2, 3, 4, 5. Carbon is number 6. Therefore, 6 protons, 6 electrons. 1s2, 2s2, and 2p, 4, 2p2. Okay? Just like that. All right? Now we must also do oxygen. Oxygen is number 8. Okay? So oxygen is 1s2, 2s2, okay, 2p, that must add up to 8. So I've got 4, 4, correct? Now let's draw them just to get a first shape, an idea. So carbon, what must I draw? Do I draw? No, you only draw these outer shell, the valence electrons, the outer shell. So carbon, okay, I'm going to go back there. Carbon back to black is 4. 1, 2, 3, 4. Oxygen. Okay, let's draw this as green. Oxygen, and here I've got to put 6. 1, 2, 3, 4. I've actually not going to do that. I am going to do it as the dots. 1, 2, 3, 4, 5, 6. Okay. Now we know it's CO2. All right. How do we arrange this? You put, let's just put in a little thingy here. Okay. The most electronegative in the middle. That's generally how we approach it, okay? In this case here, let's have a look. Well, what is, I don't have carbon and oxygen right at the moment. Carbon 2.5, oxygen 3.5. So that's not going to work in this case, is it? Okay, so let's just say, well, hang on, how do I put these together? Well, essentially what you do is you know the carbon is going to link to 2 oxygens, right? So there's going to be an oxygen on each side. So let's put the carbon in the middle, okay, shall we? Okay, let's put the carbon in the middle, right? So we've got this situation here, haven't we? And let's put the oxygens on either side, all right? We'll get back to that other bit just now. Okay, and we've got an oxygen this side as well, right? Like that. So how many parking spots have we got here? Red, we've got, there's a parking spot, and there's a parking spot. There's one, and there's one, right? So can you see what's going to happen here? This one is going to go there. That one's going to go there. This one goes here, and that one goes there. So my eventual looks like this, doesn't it? Okay. What do we have? We have the carbon. Let's put the crosses there. Okay. Those are these 4. And the oxygen, let's go back to the greens. Got a bond there and a bond there. All right. 1, 2, 3, 4. Or you could put the 2 at the bottom, really. Okay, like that, if you want to. And there they are. Okay. So what do we have? Just for completeness sake, oops, no. I'm just going to make them look the same. Like that. So we've got that bond there. Eventually, that comes down to C, double bond O, like that. Because there's 2 electrons bonding on each side. Okay? Right. Let's move along to H2O. Right. Once again, we've got, let's just do this. Okay? We've got H2O. Right? So we know that oxygen, okay, we take our oxygen, we've done it before, we go right, okay, got you, like that, and we know there's 2. So what are we going to have? We're going to have a hydrogen and a hydrogen coming in over there, aren't we? Okay, we're going to have that. That's what we're going to look like there. Okay? Water's a very straightforward one, and they move in like this. And these guys over here are our lone pairs. They are going to tell us how we shape the molecule. It's in fact going to tell us what the molecule shape looks like. Okay, that's next year stuff. Okay, the next one is aluminium oxide. Okay, let's say they just say aluminium oxide. They don't give us a formula. So you know it's Al, okay, and O. Al plus 3, OL minus 2. So I've got to balance the numbers out again, remember? So what do? I say, right, that must be 2 and 3, which gives us plus 6 and minus 6. Therefore, I'm correct. Now, how does this form? Wow. Well, let's have a look. First of all, let's have a look at aluminium. Okay. I'm just going to draw it like this. Aluminium, okay, we said is going to have... let's just put aluminium over here. Aluminium, we go and we count, okay, where he is, and it's going to be, it's number 13. Okay, 1s2, 2s2. I'm filling it up now. 2p6, okay, so that's the end. So now I've got to go to 3s and 3p. 3s2 and 3p1. So I draw only the outer shell, valence, electrons. The valence electrons I draw. So aluminium's only got 3. Okay, so let me go back and put it as black 2, 3. Let's do that, right? Now I've got to have 2 of these aluminiums, haven't we? We've got to have another aluminium. Okay, 1, 2, 3. Okay. The next step is to put in the oxygens and say, all right, let's put in oxygen. Oxygen, you know by now, is going to be, let's go to green. It's going to be 1, 2, 3, 4, right? Because I've got 3 parking spots here. Let's just recap all this. Okay. I've got 3 parking spots over here. And on this atom, also we've got 3 spots, right? The oxygen has got 2. Okay. We know the oxygen is a nonmetal, therefore the oxygen is going to take electrons. The aluminium is a metal, it's going to give electrons. So the aluminium is going to form a positive ion, okay, a cation, and the nonmetal is going to form the anion, another negative ion, anion, right? And therefore, we know that's going to happen. And we can check the delta electronegativity and see if it's polar or not. At this stage, we don't need to. Let's have a look what's going to happen, right? Well, we know that these guys are going to form because we've got aluminium oxide. It's sitting there. We burnt aluminium in air, oxygen, and we get a powder. Well, what must have happened is that must have gone there and that must have gone there. But then we say, what about this guy? And what about the rest? Well, we know for a start that we've got 3 oxygen atoms, right? So let's put in our 3 oxygen atoms. 1, 2, like so, and like so. And let's put you in as well. Might as well, hey? And let's put in your parking spots too. Okay, there we go. And there we go. Okay, well now what happens? Oh, let's just balance this whole situation. He's got one, there's a spot, and those go there. And where do you think these go? They go into there, correct? So then we find that we've got aluminium, okay, double bonded, and it looks like this, okay? Whoops, sorry. Al. Like so, okay? That's how you form aluminium oxide, okay? And the last one was magnesium chloride. No, and I've got methane still to go. So let's do magnesium chloride, shall we? Okay. Sorry. Okay. Come on. Magnesium and chlorine. MgCl2. What happens is we've got magnesium is number 12. Okay, so we fill it in. 1s2, 2s2, 2p6. And magnesium was in level floor 1, 2, 3, and it was 2 along, so it's got 3s2. There's my electrons, Mg, okay, and I've got 2. So I'm just going to put them there, which means we've got, let's put in our parking spots. There we go. There we go. And what happens is we've got a chlorine, okay, and Cl and Cl, and you know that Cl, whoops, sorry, not red, I want green, Cl has got, which goes there, and that one goes there, right? MgCl2, delta electronegativity, ionic bond, okay. Last one is methane, okay, okay. No, not green, black. Last one was methane, was CH4. Well, we put our carbon down and we know carbon, okay, it's like that. And H, we've got H is going to be all around it, isn't it? And put them in like so. And we get CH4, okay? Right, now we're going to continue in the next section with question 11, which I think I made like a multiple whole load of questions out of this one, didn't I? All right, 11, bonding sodium chloride, magnesium fluoride, ammonium. All right, this is part B, yep. And then we're going to continue with balancing equations, okay? All right, so sorry I went over the normal 30-minute tops there, but that brings us to the end, well, almost the end of question 11, almost halfway through all of these questions. Cheers, I hope it's really going down well and you're making notes and you're stopping and starting and rewinding the videos and going back and following the way we're doing it. Cheers, see you in the next one.